Hello everyone, greetings from VNR JYOTHI Institute of Engineering and Technology. This is Manohar Reddy, Assistant Professor, Department of Cybersecurity, Data Science and AIDS. Let us continue with the session of where we stopped in the previous session, CPU scheduling algorithms. Let us continue. Yes. So CPU scheduling algorithms. In the last session, we completed two scheduling algorithms. One is first come first serve and the second one is shortest job first scheduling algorithms. Now let us continue with the next scheduling algorithm, priority scheduling algorithm. So priority scheduling algorithm. So it is scheduled based on the priority of the processes. So the processes contains burst time as well as the priority of the process. So how it prioritized? So process scheduling by the priority. So in priority scheduling process are assigned a priority level and determine the order of execution. So to order of execution, it determines the priority of the each and every process. So if the process comes with the higher priority will enter into the queue first. The process which comes with the lower priority will enter into the queue last. So that mention higher priority process are executed before lower priority ones. And the main problem comes here is the starvation risk. The algorithm lead to starvation. So where low priority process may be waited for longer period of time, still the higher priority process has to complete into the queue. So here the process may wait indefinitely if a higher priority process continuously arrive in the queue. So let us see CPU allocated to the process with the highest priority and the lowest priority, the example. So here the process 1 contains the burst time is 10 and the priority given third position. And the process 2 contains the burst time 1 millisecond and the priority gives 1. And the process P3 contains burst time 2 and the priority 4. And the process 4 contains burst time 1 and the priority 2. So now they given the burst time of the each and every process and the priority of each and every process. So now how we can do this all for the priority scheduling process. So let us consider the table, the process 1, process 2, process 3, process 4. So the burst times of process 1 is 10 and the process 2 is 1, process 3 is 2 and process 4 is 1. And the priorities, the main thing we have to consider is priority. What is the priority for the process 1 is third priority and for the process 2 the priority is 1 and for the process 3 the priority 4 and the process 4 the priority is 2. So here out of these all four priorities, the first priority, highest priority comes for the process 2. So the higher priority process P2 has to enter into the queue first. So we have to schedule the process P2 as it having higher priority, we must enter into the queue. And the lowest priority is P3 which having the priority is 4. So the P3 has to move into the queue which is last after all the processes. So the higher priority of the process is P2 and the lowest priority of the process is P3. So now how we can move into the queue? Let us draw this Gantt chart diagram. So the highest priority of the process is what? P2. So let us move into the P2 into the queue. The next the P2 arrived at 0 and the priority is 1. So the burst time is 1. So it completed the time, it completes that execution time at 1 milliseconds. The next highest priority is what? The process P4 which is having the highest priority after P2. So the P4 has to move into the queue. And the burst time of P4 is 1. So the P4 the burst time of 1 is added to this 1. So 1 plus 1, 2. And then next the next higher priority process is what? P1 which is having 3. So move that P1 into the queue. The burst time of P1 is 3. So the 3 will be added to the 2. So 2 plus 3, 5. Then similarly, the lowest priority of the process P3 is having 4 priority. So the priority of this process has to move into the queue P 4 P1 and P3, and here you can see the burst time of the P2 is what? 1, which will be added, and the burst time of the P4 is what? 1, which will be added to 1, so 1 plus 1 2, and the burst time of the P1 is added 10, that 10 will be added to this one, 2 plus 10 is 12. The next the P3 burst time is what? 2, so that will be added to 12, so 12 plus 2 4. So this is the way of drawing the Gantt chart diagram from the base process entered into the queue. So from this we can calculate each and every process completion time. So what is the completion time for P1? So CT completion time for P1 is what? 12 milliseconds. So we have to calculate, we have to see the each and every process completion time at the end of each and every process. So for the completion time of process P1 is 12 milliseconds. Completion time for process P2 is 1 millisecond. Completion time for process P3 is 14 milliseconds. And completion time for process P4 is 2 milliseconds. So total completion time, this one, and from this completion time we have to calculate the turnaround time. So turnaround time equals to completion time minus arrival time. Completion time minus arrival time. So for each and every process, what is the turnaround time? So turnaround time for P1 equals to completion time of P1 is what? 12 milliseconds, and arrival time is 0 automatically. And for the P2 completion time is what? 1 milliseconds, arrival time is 0. And for the P3 completion time is what? 14 milliseconds, and arrival time is 0. And for the completion time of P4 is 2 milliseconds, and arrival time is 0. So calculate all these things. So 12 plus 1 13 27 29 milliseconds. 29 milliseconds is the total turnaround time for all process. The next what we have to find out, average turnaround time. Average turnaround time equals to total turnaround time. Total turnaround time divided by total number of process. Total turnaround time is what? 29 milliseconds divided by remaining 4, total number of process 4. So what is the 29 by 4 is 4 7 2 28.425 7.25 milliseconds is the total turnaround time for all the processes. Similarly, we have to find the waiting time. So waiting time equals to, the formula is what? Turnaround time minus burst time. So waiting time for the process P1, equals to, the turnaround time for process P1 is what? 12 milliseconds minus burst time of P1 is what? 10 milliseconds. Similarly for the P2, turnaround time for P2 is what? 1 milliseconds, and the burst time what? 1 milliseconds. And the turnaround time for P3 is what? 14 milliseconds, and the burst time is what? 2 milliseconds. And the turnaround time for P4 is what? 2 milliseconds, and the burst time is what? 1 milliseconds. So calculate all this. 12 minus 10 2 milliseconds, and 1 minus 1 0, and 14 minus 2 12, and 2 minus 1 1. So total 15 milliseconds. So total waiting time equals to 15 milliseconds. Now calculate average TAT, average WT, average waiting time equals to the total waiting time divided by total waiting time is what? 15 milliseconds divided by total number of process 4. So equals to 4 3 12 and 4 7 28 5, 3.75 milliseconds. So this is the average waiting time for all the process, 3.75. So like this, in the priority scheduling algorithm, we have to notice that the highest priority of the process has to enter into the queue first, and the lowest priority of the process has to move into the queue last. So according to this, the highest priority process comes into the queue first, and the lowest priority has to wait till all the highest priority has been moved to the queue. The next scheduling algorithm is round robin scheduling algorithm, which is preemptive scheduling algorithm. We can call it as the preemptive scheduling algorithm. Why we can say that? The preemptive nature is nothing but the process has been utilizing the CPU for some time. After that, it gives the CPU utilization for the next process. Again, it utilizes the CPU for the next time. So like that, it follows the principles: use the CPU, use the CPU, leave the CPU, again use the CPU. So use the CPU, leave the CPU, and again use the CPU till completing its burst time. Till it completing its burst time. So from this round robin scheduling, what is the main advantages and what is the main disadvantages we can see. So the main thing is what? Fixed time slice allocation. Round robin scheduling works based on the fixed time slice allocation. That means it works based on the time quantum or time slice. So we'll give the time quantum or time slice for each and every process to utilize the CPU for the 2 milliseconds or 5 milliseconds or like that. So here round robin allocates a fixed time slice, typically 10 to 100 milliseconds to each every process, and that ensures that fair CPU time distribution. The main thing is this time allocation is for the fair CPU distribution for among all active process. Only for the CPU fair distribution process, this time allocation is given to all the process, and ideal for time sharing systems also. And this algorithm is particularly effective in time sharing systems. So based on the time sharing systems, it will particularly executed, and it allowing multiple users to interact with the system simultaneously without noticeable delays. And it prevents the starvation also. So the main problem which occur in the priority scheduling algorithm is what? Starvation. So whenever the higher priority process is executed, the lower priority process has been waited till it completes. So that that starvation prevents here, because the CPU distribution is given to all the processes. So by cycling through this process, round robin prevents starvation and ensuring all the process receive the CPU time, which is crucial for the system responsiveness. Right. So because of this, round robin scheduling works. So it works based on the time slice allocation for each and every process, and ideal for the time sharing systems, and preventing the starvation process. So wherever the priority scheduling starvation occurs, that starvation prevents in this round robin scheduling algorithms. So here the example, the number of process that given is P1, P2 and P3. And the P1 is 5 milliseconds, and for the P2 is 4 milliseconds, and for the P3 is 2 milliseconds. This is the burst time of each and every process, and the time slice, time quantum that they given is 2 milliseconds. So for all three process, they have been utilizing the 2 milliseconds for each and every time. So that means P1 has to utilize 2 milliseconds, leave the CPU, and P2 has to utilize the 2 milliseconds, leave the CPU, then P3 has to utilize the 2 milliseconds, leave the CPU. If their burst time is over, then it is not ready for the allocation of the CPU for the next time, because their burst time is over. No more time is allotted for the process to allocate the CPU. So how it works, we'll see in this example. So in this round robin example, they given the burst time of each and every process and time quantum for each and every process. So how we can do this all? So that based on the time quantum, how many times the process has been utilizing the CPU. First thing we have to notice that how many times of CPU that has been utilizing the CPU based on the time quantum. So based on that, the process P1 having the 5 burst time. So based on the time quantum, it divides. So what we have to do, the step 1 is what? Divide burst time into time quantums. Divide burst time into time quantums. That means P1 5 milliseconds divided into time quantums means 2 plus 2 plus 1. That means 3 times P1 has to utilize the CPU. So 3 times P1 has to utilize the CPU. Then next for the P2, 4 milliseconds. That means 2 plus 2. That means P2 process 2 has to utilize the CPU 2 times. And for the P3, 2 milliseconds. So 2 milliseconds means it has been utilizing only 1 time CPU. So now draw the Gantt chart. So to draw this Gantt chart, first we have to move the P1 into the queue. We have to move the P1 into the queue. So P1 move to the queue. The arrival time of P1 is what? 0, because they are not given any arrival time for the process. So by default, all the processes having the arrival time is 0. So now the P1 is entered into the queue and the time quantum is 2 milliseconds. So the P1 is entered and it is using the 2 milliseconds for the CPU utilization. So in between these 0 to milliseconds, is there any other process arrived? Yes, obviously there is no arrival time for all the process, means all the processes are arrived at 0 milliseconds. So that means in between these 0 and 2 milliseconds, all the three processes P1, P2, P3 have been arrived. So we have to move each and every one. So P1 is moved. So P1 is moved and it utilized one time, and next moved P2 into the queue and it is utilizing one time. So 2 to 4 milliseconds. So again the P3 has been moved. So P1 is over one time, P2 is over one time. Now P3 is moved into the queue. P3 is moved into the queue, utilized 2 milliseconds. So P3 is also over. Now P1, P2, P3 entered into the queue. P1 utilized one time, P2 utilized one time, P3 utilized one time, and P3 completed their burst time also. So there is no more options to utilize the CPU for the P3 process because the burst time of the P3 is over. Now only P1 and P2 have left 3 times for utilization of the CPU. So now which process comes? Because the process utilizing the CPU is coming from again P1 onwards. So P1 is entered into the queue. It is utilizing 2 milliseconds, that is 6 plus 2, 8 milliseconds over. The next P2 entered into the queue. So P2 is utilizing 2 milliseconds, entered into the queue, and it completed their burst time also. And P3 is no more over, no more here to utilize the CPU one more time. So P1, P2 is over, and remaining P1 is left over to utilize one more time. So move that P1 into the queue. Move that P1 into the queue. So the remaining burst time is what? 1 millisecond. So that will be added into the 10. So 11 milliseconds. So this is the way the process have been utilizing the CPU for the utilization and leaving the CPU for the next process, and again utilizing the CPU for completion of their burst time. So like the way we can give the ideal CPU for the next process, and we can give the priority for the next process, and we can prevent the starvation from the next process also. Now we have drawn this Gantt chart diagram. So based on this we can find the completion time for all the process. So completion time for P1. So how we can identify where the last, it is moving from the right to left manner. It is moving from the right to left manner where the process have been completed their last particular point. So here the P1 is here, P1 is here, and P1 is here. But where it is completed exactly? So P1 is completed exactly here. So now the P1 completion time is what? 11 milliseconds. And similarly P2, where it is completed? P2 completed here, P2 completed here. So where it is completed? The completed time is what? Here. P2 completed time 10. And similarly P3. So P3 utilized only one time. So where it occurs here. So the 6 milliseconds is the P3 completion time. So now completion time for all the process P1, P2, P3 we know. Now what we have to do? We have to calculate turnaround time for each and every process. So turnaround time equals to, what is the formula? So turnaround time equals to completion time minus arrival time. So turnaround time for each and every process. Turnaround time for process 1 is what? Completion time minus arrival time. So arrival time is obviously 0. So 11 minus 0 equals to 11. And completion time for P2. Completion time for P2 is what? 10 milliseconds minus arrival time is 0. So 10 milliseconds. And completion time for P3 is what? 6 milliseconds minus, and the arrival time is what? 0. So total 6 milliseconds. Now calculate total, find the total of these all. 27 milliseconds is the total turnaround time. So from this we have to find the average TAT. Average TAT equals to total turnaround time divided by total number of process. So total turnaround time is what? 27 milliseconds divided by 3 milliseconds, that is 9 milliseconds. So 9 milliseconds is the average turnaround time. And the waiting time, from this we have to calculate what? Waiting time. So waiting time equals to, the formula is what? Turnaround time minus burst time. So turnaround time for minus burst time. So waiting time for P1 equals to, the turnaround time for P1 is what? 11 milliseconds minus burst time is what? 5 milliseconds. That is 6 milliseconds. And similarly for the P2, turnaround time is what? 10 milliseconds minus burst time is what? 4 milliseconds. So that is 2 milliseconds. And for the P3, turnaround time is what? 6 milliseconds minus, for the P3, turnaround time is what? 6 milliseconds minus burst time is what? 2 milliseconds. For the P2, the burst turnaround time is what? 10 milliseconds and the burst time is what? 4 milliseconds. That is 6 milliseconds. So calculate all this. 6 plus 6 plus 4, that is 12 plus 4, 16 milliseconds. So this is the total waiting time. Total waiting time. So from this we have to calculate what? Average waiting time. Average waiting time equals to total waiting time divided by total waiting time divided by total number of process. So total waiting time is what? 16 milliseconds divided by total number of process 3. So what is the 5.3 milliseconds? So 3 5 is 5.3 milliseconds. This is the total waiting time, average waiting time for all the process that they have been utilizing the CPU. So this is the way the round robin scheduling works. So the main thing is what? Round robin scheduling works for the prevents the starvation of the priority scheduling algorithm, and the ideally is the CPU. So make the CPU to be ideal for the some time, and the times quantum allocation of the each and every process. So this is the way of understanding all the scheduling algorithms. So the scheduling algorithms are two types: preemptive scheduling and non-preemptive scheduling. So all these non-preemptive scheduling are like FCFS algorithms and SJF algorithms and priority scheduling algorithms. And the preemptive scheduling is only round robin scheduling algorithm. So comparisons of all these algorithms. So FCFS algorithm is simple but long waiting time. So it has been waiting so much time, and it is simple algorithms. So the first whichever the first process arrived into the queue, that will allocate the CPU. And the SJF, shortest job first algorithm, minimum waiting time but burst time prediction is needed. Burst time prediction is needed. So if not burst time, if it is not burst time, we cannot schedule the processes for the algorithm, because the scheduling shortest job first scheduling algorithm works based on the burst time. So burst time is not there, then it is not at all works or not. And the priority scheduling, important tasks are executed first. So that means higher priority tasks are executed first, lower priority tasks are executed next. And round robin, fair CPU sharing for all the process. So fair sharing, fair distribution of the CPU for all the process, and prevents starvation, and ideal for the CPU for some time of giving the chance. So here the arrival order, advantage is simple, disadvantage long waiting time. And for the shortest job first, the minimum waiting time is advantage and hard to predict the burst time. And priority scheduling, it is the highest priority rule, and important jobs are executed first, and the starvation possible is a disadvantage. And round robin, time slice for each and every process, fair distribution for all the process, and more context switching. So this is the way of comparison of all the algorithms. So these algorithms are decides that which scheduling algorithm is the best one to utilize the CPU. So I hope all of you understand these CPU algorithms. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.